Hey everyone, in this video I'm going to go over a snake game that was built in Logisim. So this is the display right here. We have a 16 by 16 LED matrix. Above it we have a score counter, and below it we have a keyboard for keyboard input. So I'm going to go ahead and run this. We have a snake moving, and then you collect fruit, and your body length increases, and when you hit your body the game ends. Built in I have a wraparound, so if the snake goes to the right over the screen it'll come back on the left, and it's the same story for the top. Yep, so this is the snake game. Let me go into depth now with each module that I have. I will zoom out real quick to show you this. I'll show each of these parts and how they work. Okay, so now with this zoomed out view we see a few modules that I have here. On what we saw before is the display module. Up here we have a program running. We have an instruction ROM and then a program ROM that I wrote. And this sends control signals to the rest of the program, the rest of the modules. Below that we have a direction controller that'll take the keyboard input and send out the next head location for the snake. And then below that we have body memory, which is saving where pixels should be on the screen for the snake itself. And then we'll have below that we have a random dot generator. To the right of this we have a game logic block that computes when you have a point added, when you have a loss condition, and when you have an error condition. And then to the right of that we have a debug module, which is just displaying the dot location, head location, error count, point count, and loss count. So let's go ahead and start now by just showing the in-depth description of the display module. Okay, so looking at the display the display module, we have in terms of what's being output from here, we have the keyboard from the user input. That keyboard out is then going into the direction controller module. And then for an input we have a display line. And basically how that's being received from body memory, which actually body memory is actually routed into game logic, but the display line remains the same. And how this is working, let me zoom in. I'm taking one line of display memory from my body memory module and loading it one line at a time. And this is what this rank input is for. So that's also why I have two sets of registers. I have a final update register and I have a row update register. The row update reads one line of memory from the display line. It'll go through all 16 rows, and when that is done then we'll update the final register. So I go ahead and open one of these up. It's not very exciting, but basically I have each input here on the left, outputs on the right. They're each 16 bits. And then I actually have another submodule, which is a 16-bit register. So let's open this up. And these are all D flip-flops. So we have the 16-bit input, and when the current rank is being read, then these will not be undefined, and they'll actually be a value, and body memory will be saved in here, as you'll see here. So let's zoom back out. And yes, so that's essentially the display module. So now let's go ahead and look at the where the output of this goes, the keyboard out. Let's look at where that goes, which is the direction controller. So zooming in here, we have the keyboard output, and the way Logisim is set up with this keyboard is every character in there, the output is a 7-bit ASCII value. So we have that 7-bit output headed over here. And we have two comparators, a 61 and a 64. Those are in hex, but those are the those are the ASCII values for A and D, the A and D keys. So when an A key is pressed, we have the left triggered, and when actually maybe I have these mixed up, but anyway, when the D key is pressed, then we have the other direction triggered. In this direction controller, we'll calculate the next at head position. Because the snake is being led by a head, we don't need to worry about controlling the body, obviously. We just need to worry about where the next head will pop up. And yeah, so that's going to be the head output. So let's go ahead and open up the direction controller real quick. We don't have to worry about everything up here. This is for the future direction, which I never ended up using. But down here is the direction controller. It's a mess of logic, but it basically consists of the turn left input that we saw outside, the turn right input, Those are recorded with some latches here, and also actually a flip-flop, or I guess register in this case. But yeah, so we're recording those, and then we have a direction counter. So a 1 could be snake moving right, a 2 could be snake moving up, 3 moving left, down, and then 0 moving down. And this logic just calculates which way to increment the counter. We can either increment it if you want to turn left, or decrement it if you want to turn right. So that direction counter number is demultiplexed into my two x position and my two position counters. I have an x position counter and a y position counter, and those are then concatenated into the head location output. So we have 4 bits dedicated to the x location and 4 bits dedicated to the y location. And obviously when you decode a 4-bit number, you can have 16 different options, which is perfect because you only have one location for a head on a 16 by 16 or on a 16 bit line on the matrix, on the display matrix. So these counters work out perfectly. All this direction number does is determine which position counter you increment or decrement. Notice that given that we're moving right, or actually moving left, we're constantly decrementing the x position counter. Okay, so that's the direction controller. Let's go ahead and exit back out to the main. Let me zoom out. Okay, so we're going to follow this head output, and head basically goes to body memory. Notice I have head -1 here, and that was because I had a bug previously. So I'm not actually using this head location for this. So yeah, we're following this head output, and the head is going into body memory, the body memory module. And how this is being loaded is depending on the score counter. Wherever that head location is in memory, the corresponding memory address, we'll add the score counter to that location. And we have two outputs, or two directions the output's going to. We have one that's going into a shift register, that's how we're reading each the body memory line by line. And we're basically comparing that number in there and saying if it's greater than 0, then we'll consider that a body location. And we have the other line going to a subtraction line. So remember that we're putting in the number of the current score. And then after we do that, we're going to go through all of memory, and if that number is greater than 0, we will decrement it. And that's going to be 1 decrement per frame, and you can imagine as you keep decrementing, eventually the snake body will go to 0, and it will no longer show up on the output. And that serves as, it pretty much creates the functionality of the snake disappearing after a certain pixel has been there for so long. Okay, so that's body memory. Now let's go, let's kind of follow this. And then, so we have body output, which is a 16-bit row of data for the body. And we have that going into the game logic module. So let's zoom in here. Okay. Yeah, so body is going into here. And basically this is our game logic for all of the win-loss conditions and error conditions. And it also is where we route the display line to the display module. So notice we have the dot location, head location input, the body location from here input, and then we have the rank, which is, again, which rank of the row or of the matrix we're reading right now. And then output, we have a plus, LE, which stands for add point, a loss condition, and error condition. And those all trigger either reset, incrementing the score counter, or recalculating the random dot in case of the error condition. So let's go ahead and open this up. So we'll see here I have this organized. On the top left we have all the inputs just routed to tunnels, so we can use those somewhere else. On the right we have the 3 conditions that we're paying attention to in terms of snake. On the top we have, what is this, head and body, so we're figuring out the loss condition. Basically just saying if the head is equal to the body location, then we'll send a loss condition. Below that we have the body and dot location. And that's to test an error. So if say your snake's, 60 pixels long, you might be taking up a lot of the screen. And if you have a random dot appear on your body, you don't want to have to sit there forever while your snake goes over it to actually see the dot. So we have it basically recalculating a random dot in the case that you generate a dot that's already on your body. And then below that we have the new basically the eat condition where your head is overlapping with the dot. And this is a simple if dot is equal to head, add point. So that's pretty simple. The only things down here to explain, we want to, so given that dot is a single location on a 16 by 16 matrix, it doesn't necessarily appear on the same rank as the body being red. So we only want to really compare dot or head with body when the rank is the same. So we're always inputting, we have a rank input to a lot of these modules. That's just to make sure that we're always only measuring a dot or head location when the body rank is the same. And we do that for the dot and head. And I just renamed those dot filtered, head filtered. Okay, so that's the game logic module. Let's go back out. Okay, now we're actually going to get to the cool part. So let me cut the video and then we'll get to the snake program. Okay, so let's look at the snake program that I'm running right now. This module, to start out with, the outputs are these control signals labeled 0 through 15. And if you haven't seen by now, those are scattered throughout, connected to each module. And that just determines when that basically is controlling my timing for the whole snake program. To the left of that, I have an instruction ROM, which just holds my instructions that I made to control these. And then I have a program which is calling those instructions. So I actually made a document, a spreadsheet for this. On the left, we have the control signal labels. So 0 is the buffer enable for retrieving head size, etc., etc. You can pause the video and read this if you'd like. Maybe I'll pull this to the side just to make it easy to read. And then on the right, we have, let's go full screen, never mind. Okay, and then these are the functions, or the instructions that I'll call. Update and place head in memory, load body memory into line register, row update, screen update, repeat program, skip next instruction. And then we have the address location for where they're stored in that instruction ROM. So we have this stored at address 0, this stored at address 4, address 29, 2B, FF, and etc. And then down here we have the binary code, or the hex equivalent of this binary code up here. And that's just so we can control the control signals with a hex value, because that's how we write that in the ROM. So this is the kind of the information about that. Let's go and open up the ROM. You'll see here, if you want to go back and compare this to my sheet, I have whatever that was at address 0 stored here, etc. And basically 0 is a stop code to call the next instruction, or call the next program instruction. Okay, and then we have in the program ROM, we have a program that I'm running calling different instructions. I'll actually pull up that list in a second. Yeah, in this picture, oops. Okay, so in this picture, I actually have what program I'm running in there. Let's zoom in. And basically I have, let's go full screen, yeah. Okay, this is my line number, and then I have the opcode that I'm using, and then I have a description of that, and I have the picture of that ROM right here. Basically what I'm doing to start out my program, I'm updating and placing the head in a new memory location. After that, I'm going to go through and load all of the body into the register, which takes a lot of time given I'm doing it row by row. And after that, well, these are actually kind of simultaneous. I'll call 4, and then I'll call 28. I'll call 4 28 16 times each, basically because I want to load the row register when I have the body data accessed. And then after that, I'm going to update the final register, which is actually going to print a new frame. And then after that, I'm just going to repeat the program. And you'll see here, these opcodes that I have are listed in my program. And this is just going to be repeating. Like I said, FF is repeat, or not in this case, FF is the stop code. So FF will just loop back to 0, and yeah, it'll keep doing this. It's running on a loop. Okay, so that's the instruction, and that's basically it. Okay, so I was in the middle of editing the video, and it turned out that I didn't really get some good gameplay of this, and I also didn't quickly go over the random dot generator or the data probes, so I'm going to do that real quick. So just going over the random dot generator real quick, opening this up, we have, it's really not much. I built this up to separate the x and y coordinates initially, but turns out I didn't need to do that. In the same way that I'm showing the head, I'm also showing the dot with an 8-bit 4-bit X, 4-bit Y location, as you see here for A and B. And all these are hooked up to are two random dot generators here, which is a thing that's built into Logisim. So it's nothing that I really had to create. It's just they were nicely built in for me. So this easily could have been replicated just by doing a 8-bit random dot generator, not even having the submodule. But this is what I have so far. I haven't bothered to fix it, but this is what's inside. Okay, and then going to the debug module. There's really nothing to it. I just have displays for the dot location and the head location, and then I have counters to count how many error conditions I have, how many loss conditions I have, and how many add point conditions I have. And the reason for this is just so I was able to debug my project, because it didn't work perfectly at first. So I needed to actually make sure that all of my values, so the values appearing on the screen in memory, and the ones I was calculating with the controller and random dot generator, I had to make sure that those all matched up. So that's what that was for. Okay, so I'm just going to go ahead and play the game now. I will start off from the beginning. I will go ahead and play through until I have a loss condition. In that case, the game will reset, and that is that. So thanks for watching. If you have any questions, go ahead and leave them for me. I might add some other projects I have, other projects I've built in Logisim. I might add some of those on YouTube, so we'll see. But yeah, thanks for watching.